Hello everybody, my name is Tefik. Today I'm going to present part number 2 of our video series, which is the API collapse regimes. Before I go into that one, let's recap what we have done in the part number 1. So we have derived the Barlow equation, API uniaxial burst from tangential stress by setting the radial and the axial stresses to 0. So the main caveat with the equation was basically axial stress isn't considered. And also we have done the derivation for the thick wall equivalent or biaxial equivalent, where we considered the radial stress as well in addition to tangential stress. We could see that the burst rating was slightly lower, but they were very similar. And also we made a brief introduction into the design limit clause. So today, as I mentioned, part number 2 is our topic, the API collapse regimes. So again, I left the design limit plot in its original position, so we can refer back all the time. So today, in the part number 1, we were considering the upper portion for the burst, where the delta P is positive, internal minus the external pressure. And today in part number 2 we will be covering the bottom part of the design limit plot, where the delta P is negative, so the outer pressure, external pressure is higher than the internal pressure. As you can see, the the ellipse is here, and then you have the uniaxial rating. So this is the uniaxial rating for collapse. Obviously, you can call it as a design factor of 1, and then if you increase the design factor, it will go this direction. You can notice this part over here that I basically shaded with red. That's the part where the tension is affecting the collapse rating, i.e. tension is rating the collapse rating. This is independent from the yield strength duration because of the temperature. So that's the basically we calculate a corrected yield strength in this area with the effect of tension or post and the backup pressure, either is internal or external pressure, and then together with the tension we calculate revised yield strength, and then we put that revised yield strength into the bunch of collapse equations once again to find the revised collapse pressure. So that's why this dashed line tends to come down, and then basically it will join into this tension uniaxial tension line at the x-axis. Okay, so let's start with the collapse regimes. So the collapse regimes is mainly a function of yield strength and the wall thickness. The wall thickness is the nominal wall thickness, as we discussed last week, and yield strength is also the yield strength in the elastic region, where basically the slope is the Young's modulus, the stress over strain, if you remember from part 1. So it has 4 regimes: yield collapse region, plastic collapse region, transition collapse region, and the elastic collapse region. So here you have a outer diameter over thickness and on the y-axis, and the yield strength on the x-axis. And here you see there's 4 distinct regions here, and then there is a kind of a separation between each collapse regime according to the yield strength and the function of a yield strength and the outer diameter divided by the nominal wall thickness. So the lowest one is the yield strength, yield collapse region, and then the plastic, and then the elastic, and the transition. So today what we are going to do is we are going to look at the derivation for the yield collapse, because as far as I know, the rest of the regions were basically number fitted based on some specimen test, some physical test. However, the yield collapse region, we could derive it. So how are we gonna derive it? So we pull the tangential stress equation from last week, the one of the principal main stress, and then still the radial and the axial stress is 0 here. So this time is the internal minus the external pressure. We know that it is delta P. However, we are concerned about the collapse, so that will be a minus of this one. So whenever we find the minus delta PO, we will convert with a multiplication of -1 to convert back to collapse pressure or collapse rating. So let's evaluate this tangential stress in the inner wall again. That's the inner wall, so they will cancel each other. And then we basically end up with this equation where we have the outer pressure, outer area, inner area, and the outer area. So that's basically a cross sectional over here. And then, as we mentioned last week, it's basically to be able to make it look like the yield collapse equation, we need to convert all the radiuses into diameters. And because it's the 1/2, you can basically cancel the 1/2 squares on both sides. So we can easily write the radius square into the diameter square, and then and the same of the cross section into diameter and the radius. So, and then here what we're gonna do is we will use the same conversion again. Inner diameter is outer diameter minus the 2 wall thickness. That's the nominal wall thickness again. We will discuss this further into the I think part number 4. And once we do the conversion of the inner diameter, you can see that the outer diameter squares, outer area is cancelling each other, and then we are left with this equation. And then what we need to do is we need to multiply both sides by 1/wall thickness square, so that we end up with yield strength is equal to tangential stress, because we evaluate the tangential stress, the others are 0. And then we are looking for a yield limit, and then we end up with basically diameter, outer diameter divided wall thickness square divided by 1 minus outer diameter divided by wall thickness square, and then there is a outer pressure, and then there is a 2 left here. So we basically we turn the equation upside down, and then we know that there's a minus here, so we need to correct back to get a collapse rating of 2 times the yield strength, and then times the outer diameter divided by the wall thickness, nominal wall thickness -1, divided by the ratio of the outer diameter to wall thickness to the square. So this is the yield collapse rating. So that's the yield collapse rating to define a rating in this region, in this lowest region. So what I will show you on the spreadsheet is when we look at the ellipses is you can basically take your grade pipe, you know, if it's either L80 or P110 or K55, whatever, and the poundage. And then what you can do is, depending on the wall thickness and the yield strength of the pipe, you can basically plot this pipe into this one of the regimes, and then it's gonna plot it according to its to the limit of each collapse limit that I'm gonna talk about just in a second. So here I put an example of 958 L80 53.5 pounds per foot casing, and then it falls into the plastic collapse regime, not in this one, the one above. So this of course this collapse yield collapse rating is only applicable to a certain outer diameter divided by thickness ratio. That's basically defined by bunch of terms defined by ABC, which I put it on the second page. They are dominantly impacted by the yield strength of the pipe basically, which I'm going to show on the next page. So now the next region is the plastic collapse. In blue here is the plastic collapse where the R958 lays in, and then you can basically plug this equation, and then here you see the wall thickness. That's the nominal wall thickness, and then you should be able to come up with kind of a spec value or very close to the spec value. Sometimes vendors tend to round it down, or if they have a kind of an improved collapse rating, well, they need to I think document it. Okay, so let's go to the second page. So if we continue our regions, so we have, you can ignore this part for a moment. So we have the transition collapse, and we have the elastic collapse from bottom to top. And there, of course, outer diameter to thickness ratios is a bit getting higher. So basically, the pipe is getting a bit thinner to the top, and you see all the ABC, all the constants that are mostly impacted by the yield strength over here, Y's, and you can see all the collapse limits. They are basically dominated by the outer diameter divided by the nominal wall thickness. So, and again, your pipe, when you put your pipe grade, is a quick cross check across the vendor's spec sheet. It's always good to cross check, if you can, of course. So on the right hand side, what I'm gonna discuss is the design limit plot again. So we discussed that this part over here that is impacted by the tension, and of course the combination with the backup pressure. However, when we look at the equation needs to, I think, it looks similar to you. So there's a 0.75 and 0.5 here, and the ratios are basically whatever the tension plus the backup, and then that's the ratio to the yield strength. So that's important, and then you come up with a yield strength asterisk, with an asterisk or a star. So that will be the reduced yield strength. So when I say reduced yield strength, the yield strength doesn't reduce with tension. Realistically, it's kind of a correction to the yield strength, so that we can feed this yield strength back into this four collapse regimes: yield, elastic, transition, and plastic, and then come up with those revised A, B, C, F, G values again, and then also recalculate our collapse rating. That will be the collapse star. So usually I think some might prefer not to use the collapse load cases, and then not prefer to use the traction for the collapse load cases. However, some might want to use the the traction load cases for the collapse load cases. As you see, the uniaxial limit is exceeding the traction limit on this region when there is a high tension on there. So, and then after that, I would like to talk about this 2008 or pre-2015 API. I think it was 5TR5C, I believe. Correct me, please. But in this one, for example, there is a major difference, because in the new API formula we have this internal pressure as a correction for the yield strength. However, on the previous API TR3, I think it was kind of there was a correction factor into the internal pressure, so that we were derating the internal pressure. So what happens is, your collapse differential, let's call it. It will be looking higher with this one because we were downgrading the internal pressure. But in the 2015, because we are already accounting for PI here, what it is basically your collapse differential is external pressure minus the internal pressure. So that's I think major difference. And here I felt that in the burst when we were covering the burst in part number 1, and then now we covered the part number 2 in collapse. We didn't talk about a lot, about the load cases. What I want to point out here is for example, I put simple schematics here. So these are, let's say, installation loss, or not installation loss, but post-installation loss, let's call it. The casing is run in cemented place, and then we are drilling the next hole section. So here, for example, I put like a common collapse load case of loss returns, or it could be full evacuation in the worst case. But in the loss returns case, what happens is the fluid tends to equalize when you are drilling the next hole section, tends to equalize to the next section's pore pressure, depleted pore pressure. And what I want to emphasize here is when we take the delta P, when we look at the pressure differential of external pressure minus the internal pressure, some guidelines do say that the external pressure is basically mud weight that casing was running whole, because it will maximize the difference, right? But some might say use a different gradient in the cemented interval, and then depending on the fluid level, where the fluid level sits, the collapse load or the external minus the internal pressure load differential might be anywhere in the well. So I just want to point out that the external pressure profile is quite important. So I say internal pressure profile and then external pressure profile. That will affect whichever external pressure you work with. It's going to affect your pressure differential. And of course, now this is a uniaxial. We are talking about the uniaxial collapse load case here, okay? Where we take the differential, and then we are not covering the axial profile here, which we are going to cover on the next part number 3. However, what I need to say is because we have this duration here, that the collapse rating of the casing, if there's a tension, of course there will be some tension depending on where we are on the casing when we talk about the true tension and the initial conditions tension profile. You will have the collapse rating derated, and in addition, of course, if you have a different temperature profile from initial conditions, then yeah, you will have the temperature duration effect on the yield strength. So that's the kind of main one of the main collapse load cases, and of course during the well construction process. And I move to left. That's the kind of one of the quite common burst load cases. I take a frac at shoe and then minus full gas column. So when you drill the next section, of course, you can just look at your kick tolerance or third to fourth barrel kick, and then of course that's how you evaluate your casing shoe for your FIT or leak off test. But you could also use that one to come up with some burst loads on your casing. However, this one is kind of a severe case where you have the fragate shoe and then minus full gas, because the shoe is I imagine is very strong here. So what I need to say here is the internal pressure profile, we can come up with it. There's a gas, of course, when we take the compressibility effect of the gas between the pressure and temperature, we can come up with the internal pressure profile. However, the external pressure profile is a bit more tricky. So if you remember from the lectures, we tend to say, yeah, we tend to have a maximum burst, close to surface, but it same as the collapse. It really depends, because your external pressure profile, some companies might tend to use kind of a pore pressure across the cemented interval as an external pressure profile, or some companies might say, okay, I'm gonna go use the mixed water gradient, or I'm gonna still use the mud weight that was running hole in this where there is basically old mud from the previous hole section. So what I try to say here is the external pressure profile is quite important. If you just look at the uniaxial, like just look at collapsed pressure differential or burst pressure differential. And here also, of course, you could say that the tension is also affecting the burst rating in a positive way. However, we will cover that when we come to the triaxial design. And same applies temperature, duration on the yield strength. So after I have this like a construction cases, I come into this one. So this is kind of I draw this imaginary well where basically is kind of a sealed on the well. So you could call it a subsea well where you don't have access to the sea analyze. So I call it so that's the production tubing, and then that's the production casing. So in some parts of the world it's called A section, and then B, C, it goes like this. However, some regions of the world they want to call the inner section as a C section. So for now, let's call it as an A section. So and the B section and C section. So as you see, the C section cement rises into the casing shoe. So what I want to point out here is here, for example, we looked at a collapse load case where only a collapse load case. It doesn't induce too much of a burst load case. Of course, it will have a associated axial profile. And here you have the burst load case where it doesn't induce too much of a collapse. But here, what I want to share different from these two is basically any pressure here on the C section is gonna tend to collapse the inner string, and then tend to burst the outer casing. So here there's a different scenario from these ones. This is kind of as completion is run, production packer set, etc., etc. So another thing that I want to talk about, of course, the collapse and the burst load cases, as we know, don't only exist during the installation, but also when the until the end of the life of the well, until we P&A the well. So as you see, we have a tubing leak load case. That's one of the common burst load cases. So what happens is you develop kind of a tubing leak over here because of the corrosion or because of whatever reason, and then you have a pore pressure minus if you are producing gas or oil, whatever, minus the hydrostatic column, and then that pressure will apply on the top of the completion brine. And assuming that your production packer is intact, what is going to happen is your internal pressure profile will be this pressure plus the full brine hydrostatic acting on the production casing. And then of course, as I mentioned, depending on the external pressure profile, this burst load could be quite severe or might not be. And at the same time, let's look at the collapse load case with this completion as completed case, where you basically have a kind of a packer leak, and at the same time your formation is depleted. And then what's going to tend to happen is this because the packer is leaking now, it will not hold the completion brine or completion fluid, let's call it. It will tend to draw down until it equalizes the pore pressure with the depletion. And then what's going to happen is your backside of the casing is now it will induce kind of a collapse load. So again, depending on your external pressure profile it might not be just the full mud weight running hole, but it might be something else, because all the fluid over here might be degraded to base water at some point. So that's gonna induce a collapse load. But again, depending on your external pressure profile assumption, the severity of the loss might be different. Okay, so let me wrap this up. So all load cases over here, we just looked at basically very simple, in a simple point of a internal minus the external pressure, or also external pressure to the minus the internal pressure, or we had the both here. So of course all these cases will have kind of a associated tension profile, and then that's why we will build a design limit plot where you basically consider the tangential, radial, and the axial stresses, all three of them. Yeah. But at the moment we just covered these I think one of the most common load cases where you just have the delta piece. Okay, and then on the next video I will cover the axial load cases, and then we will look at some ballooning and the temperature induced tension or compression, and then we will basically make a design limit plot at the last part, which takes into account of all the effects. Thank you very much for watching, and then see you in part number 3. Thank you.